Okay, yes. Yes, thank you all for coming to the talk. Thank you for inviting me, the organizers. Thank you for actually having this event. It's really amazing. It was just like I was telling people, I was here long ago in 2018, and I have no memory of it, but I'm hoping that I'll remember something of this place this time. Okay, so yeah, like Anand said, I didn't realize until a few days ago that I was giving two talks, or so I had to decide what to do. And so what I decided to do is like, I'll tell you about two topics instead of one, because I thought 5 hours of one topic is, I could be trying your patience. I might try your patience today, but I wanted to try it only a little bit. So, so today I'll tell you about, applications of spectral methods in problems in algorithms and some problems in coding theory. And then tomorrow I will tell you about somewhat related, but really like, a different topic, which is an algorithm design using this so-called sum of squares method, and how there is like a new paradigm of algorithm design that reduces, this task of designing fast algorithms to finding, proofs. And I'll explain all of that to you tomorrow. Okay, but today, we'll talk about for the next 2.5 hours. I'm gonna tell you about this topic, the spectral refutations and their application. I'll explain everything, as it goes. So let me say that, I might have planned too much of a content, especially some of the organizers explained this to me, which means that I'll try to go slow deliberately, and I don't intend to finish all of it. That will be perfectly fine. Please feel free to stop me at all points of time, and I'm happy to go over things or use the big board that still remains even after I've used the slides, okay? Good, so let's begin. Let me tell you my goals, okay? My goal, there's like a simple goal that is usually there in the research talk to tell you about a class of results, and that is gonna be, how to solve a certain class of beyond the worst case instances of the k-SAT problem, okay? You all know that k-SAT is hard, but then there are models of k-SAT where in principle you can hope to do better, and I'll tell you about how you can design algorithms based on eigenvalues of certain matrices built out from the input instance, and you can use these eigenvalues to solve the problem, okay? So I'll tell you about this. This would be pretty much an algorithm design part of the talk. And then I'll tell you, like, there is some nice kind of a bonus that comes out of working on this problem, which is that the ideas that go into building these algorithms, the so-called spectral refutation, which just means the use of a spectrum of some matrix to design some algorithm. That's all that word means at the moment. You'll see that this idea has actually lots of other applications, which at least at the surface have nothing to do with the k-SAT or related problems. In fact, they're not even algorithmic problems. They are basically like questions about whether a certain kinds of object exists or not. But it turns out you can somehow attack those questions with the same ideas, and I'll tell you how that can happen and how at least you can prove some interesting results with this technique. Now, those are like, the research goals of the talk. And if it was a research talk, that's where I would stop. But because it's a tutorial, let me mention two ideas. And I'll likely only get to the first one in detail, given the fact that I plan to go a bit slower. But you can ask me about the second one because I still think it's like very, very cool. Okay, so the first idea, which will be a very important tool in developing these algorithms, is the use of matrix concentration inequalities. Almost everybody who goes through some kind of theoretical computer science training knows about Chernoff bounds. So you all know about large deviation inequalities or concentration inequalities. But usually we study them for scalars. Perhaps some of you haven't seen the matrix versions of this inequality. And I'll tell you like how there is basically a very natural analog which is super useful, okay? So in some sense, like, the investigation of these algorithms would be very, very neatly tied into the investigation of what are the strongest inequalities of this sort that we can prove. In fact, towards the end of the talk, I'll state a conjecture that extends this inequality and would likely imply, stronger results which are so far not known. Okay, so the second tool would be polynomial concentration, and this I'm not sure if I'll get to. If you've seen, again, Chernoff, like, both of these things can be thought of as like different generalizations of Chernoff bounds. Like one way to generalize Chernoff bounds is to, make the constituent variables matrices, okay, instead of scalars. And that's like the first tool. The second tool is, think of Chernoff bound as an inequality for linear forms, so in particular linear functions with positive coefficients. And then you can ask what happens to polynomials with non-negative coefficients, like higher degree polynomials. And I'll tell you a statement which is extremely powerful, very useful, but I haven't seen that many uses of it in at least theoretical computer science literature. Which, like the mantra that you can remember about this statement is that there are certain kinds of polynomials which you can think of as well-spread polynomials. The natural generalization of, like, the linear polynomial that you remember in Chernoff bounds, like sum of xi, okay? Such polynomials enjoy Chernoff-like concentration around the mean, just like Chernoff bounds, okay? That's basically the punchline. And I'll tell you, if I get to that point, I'll tell you this, otherwise ask me later. Okay, those are the goals for my talk. Now, there are many proofs of non-commutative Khintchine inequality, this matrix concentration inequality. I want to just point out one thing as we go into this talk. There is a very nice, very elementary proof due to trop, which is, like, I've taught versions of proofs of this inequality, which, either rely on deep statements or take me 3 lectures to build. But there is actually a proof due to trop, which is super simple. And, you can teach it in one class. If you haven't seen it, I actually teach a class. I taught one class this term. And there is like a lecture notes from this class available. You can see like a full elementary proof of this inequality. It uses nothing. In some sense, everything that is required, I prove it in the lecture. And it's like, 2 lectures, I can finish the whole proof. Anyway, good. All right. So that was the prologue. Let's start with like the first bullet point, this algorithmic question that I was talking about. Okay. So, like I told you, it's going to be about the k-SAT problem. And it's going to be a certain problem that I'm going to call refutation problem. Okay. So what does that mean? Well, in this problem, you're given as input a formula of k-SAT. Let's call it phi. Okay. This formula will always be on n variables, which have, m clauses. This is just like some notation that I'll use throughout the relevant part of the talk. Okay. Now, you typically think of this problem as like outputting either a decision, yes or no, or a finding a satisfying assignment. But permit me this, variant of it, which I'll explain to you is essentially the same eventually. Okay. Your goal is to output a number between 0 and 1 in interval 0, 1. And the meaning of this number, or the correctness guarantee, is that no matter what formula I give input to your algorithm, it should output a number which is larger than the maximum possible fraction of constraints that any assignment can satisfy. Okay? Now, if that's all I asked you, of course, you would say that, I can just simply output 1 all the time and I would always be correct. Yeah, you will be correct, but you won't be useful. The usefulness or the success of the algorithm basically is described in this line at the bottom, like, what it means to refute a formula. So refute a formula means like prove unsatisfiability of. That's what the word literally means. So we'll say that the algorithm has successfully weakly refuted the formula if on the formula phi it outputs a value which is strictly less than 1. Because given the correctness guarantee, the algorithm has given you basically an ironclad proof that the formula cannot be satisfied. Okay? And more generally, we'll think of strong refutation, which means that not only can an assignment not satisfy all the constraints, but in fact, every assignment must violate a fixed constant fraction of constraints. Okay, that's what strong refutation means. Any question about this basic setup? Yeah? Oh yeah, value is like the definition is in the quotes there. It's the maximum possible fraction of constraints that the assignment can, like, go over all possible assignment. For each assignment, ask what fraction of constraints you satisfy, take the maximum. That's the value. Okay, that's the best an assignment can possibly do. It's the number between 0 and 1. Any other questions? Yeah. Yeah, so if I output a value which is strictly less than 1, I could output in principle 1 minus 1 over m. That means that every assignment must violate at least one clause, right? If I ask you, if I make the success criteria to basically output 1 minus delta or smaller number, then it means that every assignment must violate delta fraction of the constraints. That's just a stronger guarantee. Of course, notice that, I can't expect this kind of a guarantee on every formula because some of them are satisfiable. So my goal, of course, is to design such an algorithm that, succeeds on as large a class of k-SAT formulas as possible, given that it makes sense to ask this question for them, given that they're unsatisfiable. Right? That's the only such situation where this question makes sense. Now, the way to think about this question is, if you thought about like the search problem of finding a satisfying assignment, that's a natural question to ask if your formula is satisfiable. If your formula is unsatisfiable, the natural question to ask is, give me a short proof that convinces me that the formula is unsatisfiable. That's what this question is, right? Unlike satisfiability, where you can always at least have a short proof, it's unclear whether even a short proof exists, right? Like if you've taken any complexity class, you're well aware of this fact, but notice that, the trivial proof really is to go over all assignments and check each of them, dissatisfied, but that will be exponentially large. So in here, even the output length is in question. Forget the task of finding it efficiently. Good, all right. So, this question is very well studied. So I want to tell you a little bit about, what we know about this problem in the worst case. And in order to summarize decades of work on it, I'm going to actually show you a diagram because the picture apparently speaks 1,000 words. So what this diagram is trying to do is it's plotting the number of constraints on the x-axis and the running time of the best known algorithm that we know about the problem on the y-axis, okay? Why am I doing it? Well, the main intuition is that as the formula gets denser, as you have more and more clauses, the task of refutation should become easier, okay? A priori, okay, if you have never thought about this, it can for a second appear like this is counterintuitive, but it's really not. Think about it. You're trying to prove that the formula is unsatisfiable. Every additional clause is an extra constraint for you to satisfy. So you should think of it as like, every additional clause makes the possibility of a simple contradiction arising more likely. Like that's one way to intuitively grasp why it should become easier as, the number of constraints increase. Of course, this intuition was made precise already in the 90s by a very nice work of Arora, Kargar, and Karpinski, who showed that if I have a k-XOR formula with omega of n to the k constraints, meaning a constant fraction of all possible k clauses are present in the input formula, then there is in fact a polynomial time algorithm to solve the question I asked you. Okay. So formally, for those who know this, they gave a p-task, like they basically can approximate the value of the formula up to an additive epsilon in polynomial in n1 or epsilon time, but doesn't matter for the purpose of this talk. You should just think of it as like they can basically solve the problem I asked you on the previous slide. So that's like this green portion here. Now, if you go below n to the k, then there is an algorithm that does not run in polynomial time, but it definitely beats brute force search convincingly. What do I mean by convincingly beat it? Well, the running time of the algorithm is 2 to the n to the some constant, where the constant is strictly less than 1. Okay? If you were to brute force search, you would take 2 to the n time. This is what I'm going to call as convincingly beating brute force search, having a sub-exponential algorithm. That's what this yellow part of the curve is. Okay? And then, it turns out that if you go below n to the k minus 1, which is n short of like this threshold at which Arora, Kargar, Karpinski works, then there is no known algorithm that beats, exponential time. It turns out there is a completely different story and a completely different talk one can give on exponential time algorithm for KSAT, which I'm not doing today. There are non-trivial exponential time algorithm for KSAT in the worst case, but they're still running time 2 to the constant times n. That's what my standard for brute force search today is, even though it's better than 2 to the n. Okay? Everybody okay with this? Okay. So now I describe this story as if I'm describing algorithm, but it turns out that if you at least assume this so-called exponential time hypothesis, which you should think of it as like, P versus NP on steroids, like, some kind of a trumped up version of P versus NP, which is like, let's say, believable for the purpose of this talk, then, this picture cannot be improved. Whatever is drawn in this picture is basically optimal. So there's nothing to do. This is it. This is the picture of KSAT as far as worst case complexity goes. Okay, any questions? Good. All right. So that's, something to remember. There were like 2 inflection points in this curve. At n to the k minus 1, something a little bit more than that, a sub-exponential time algorithm arises. At n to the k, a polynomial time algorithm arises for the task we're interested in. Okay? Good. There's no known algorithm, and in fact, there cannot be if you assume the exponential time hypothesis. Good. All right. So, I'm going to go back to the 90s where this word was a big hit. I haven't seen it, used lately all that much, but, I'm an old guy, retro. So I'm going to go retro and say, how do you cope with NP hardness? How do you handle hardness? Algorithm designers had a tough time handling NP hardness in the 70s and 80s. And so they, designed lots of coping mechanisms. It's a complete aside, like, I learned that cope is actually like a zinger. Like, say somebody is like very unhappy and you think that they deserved it, then you basically write to them or tell them cope. Okay, and I recently learned this when I was talking about coping with NP hardness. That's not what this is. We are not trying to stick it to NP hardness or something. We are actually still trying to design algorithms here. Okay, so what's the scope? Why can we hope to do this? Well, in worst case, we really made no model for the input instances. We really were interested in solving each and every input instance, right? You say, okay, so we've learned that maybe there cannot be an algorithm that succeeds on each and every input instance, but perhaps there can be one that still succeeds on a lot of interesting instances. That's somehow the philosophy of coping with NP hardness. And so, one specific idea is the so-called average case analysis, which, by the way, Karp invented about 4 years after he proved 23 problems NP complete. So this is not like some new invention. Like already in the 70s, Karp was thinking about how to cope with NP hardness. And he said, what about random instances? Can you solve these hard problems when the input instance is random? Like k-SAT formula, take a random k-SAT formula, right? And for k-SAT, there's a very natural random model, right? Like just literally sample each clause independently from the set of all possible clauses, which means that k-tuples are uniformly random, the literal patterns on them are uniformly random, etc., etc. Right? Just independently, just sample it from the most natural random model you can come up with. Okay. Now, you can ask what is known for this, and this is again an extremely well-studied model. People in this room have studied it very well, not just like people outside this room. So let me tell you, what's known about this model, again on the same kind of diagram so that you can compare and contrast, okay? So same, number of constraints on x-axis, running time on the y-axis, and I guess I forgot to mention, but I'm plotting exponents of n in both, so it's like a log to the base n scale, okay? So you can ask, okay, when is it a polynomial time algorithm, first of all? So in the worst case setting, there was an n to the k threshold where a polynomial time algorithm arose up to constants. Here it turns out that there is a non-trivial algorithm that succeeds as soon as you have n to the k over 2 constraints. Okay, so some kind of square root phenomenon is going on at square root of the density at which, in worst case, such an algorithm actually was possible. You can actually find an algorithm for the random version. Okay, and then as soon as you hit superlinear number of constraints, actually as soon as you have n to the 1 plus epsilon constraints, there is a non-trivial sub-exponential time algorithm. That's this yellow part of the curve, and this curve in fact was due to a work of Prasad, Satish Rao, and Stilshram. Okay, so that's the yellow part of the curve here, okay? And there is some weak evidence. I don't want to tell you too much about it. We don't have even as to the extent one can believe the ETH, I don't think we have anything close to that kind of an evidence here, for the average case. But there are some lower bounds on restricted classes of algorithms that you can interpret as saying that maybe, going beyond this picture is somewhat hard, okay? So that's what these red works are. And you can ask me later if, you're interested. Good. So, the algorithm that succeeds at this point is an algorithm that uses eigenvalues of some matrix. So it's often called a spectral threshold because it is the threshold for a natural spectral algorithm and we don't know anything better. Okay. Good. So that's basically the summary. I'm going to show you this, this formula here because I'm going to use it again later. So this is just to if I show it to you 3 times, the third time you'll remember it, right? Or you'll find it familiar. So that's like the first time. So this is just the polynomial time algorithm regime. And now what this is doing is, this is simply parameterizing this yellow part of the curve, okay? Notice that, this single parameter L parameterizes like the line from n to n to the k over 2. If you plug in L equals n, you get m, which is n. If you plug in L equals 1, you get n to the k over 2. So as L moves from 1 to n, basically m goes from n to the k over 2 to n. And, the running time of the algorithm basically is n to the order of L. Okay, that's all the parameterization there. Good. All right. So now, there is an interesting phenomenon that occurs in the average case that we have no analog for in the worst case. And that's why, I did not even have a space for this kind of a result in the diagram I showed you for worst case. But let me tell you, because it's a very interesting phenomenon. So this is like a one-of-a-kind, beautiful result due to Feige, Kim, and Ofek, that there is a regime for k-SAT formulas for any k, which is strictly below this spectral threshold, where we know of efficient algorithms for refutation, and where we suspect there may not be any better. This threshold, this second threshold is actually below n to the k over 2 by a polynomial in n. It's not a polylog gap, it's a polynomial in n gap. And at this threshold, there is in fact a polynomial size witness of refutation. What that means is that there exists a polynomial size witness, which I can hand over to an algorithm, which then will run in polynomial time, and be certain that the formula that they were given was unsatisfiable. This goes back to the comment I made earlier that in the context of refutation, even the size of refutation being small is unclear, unlike satisfying assignment. And what this is saying is that while I don't know a better algorithm than brute force search to find such a witness, if you gave it to me, I can verify it in polynomial time. In other words, there is at least a short witness of refutation that arises below this threshold. And it's been like whatever, 19, 20 years now. People have tried quite hard. I myself have tried quite a bit hard to improve this threshold or like try to move it or whatever and have failed. There is no reason why this number or why we stop here or why we can't go beyond, etc., etc. It's like it's a major open question, but we don't know how to do it. Okay. Yes. Yeah. Yeah, the delta is like it's like, there are two algorithms and it's like, you merge them and there is some kind of a balancing point and delta comes out of that. It's not mysterious at all. Yeah. We know it for every value of k. This delta k is extremely transparent. For 3, for example, it is 0.1. What do you mean? Well, no. In fact, if I had to conjecture, I would say, maybe there should be in principle a witness at n to the 1 plus epsilon for every epsilon bigger than 0. If I had to guess, 1.4 seems like a silly number to guess as the right one. It's below 1.5, so I'll guess it is 1 plus epsilon. That's my guess. Okay, good. All right. So, okay, great. So we saw 2 pictures, okay? We saw like the worst case picture and we saw the average case picture. The average case picture was much better than the worst case picture. Like, both the thresholds were shifted leftward, so the problem did get much easier. And you can ask, like, how should I think of k-SAT? Like, what do these 2 pictures teach me about k-SAT? Right? Like, your interest could have been in learning more about random k-SAT model, and then you've learned everything you can. But if you're interested in learning about k-SAT, perhaps you have to ask which model is reasonable, or perhaps both are unreasonable, right? And so, in general, like, even beyond like this question of whether it's a reasonable model, you can ask, am I inventing algorithms or certificates or ideas that are super tied down to a specific random model? Because from the perspective of algorithms, it's kind of a suboptimal choice, right? There are some investigations like statistical physics where a single random model is super important, and then that's not what I'm talking about. But in algorithms, the random model is like a means to an end. We are interested in designing algorithms. So it is really, prudent to ask, have I invented like an algorithm that is simply like based on a quirk of a specific random model that I got interested in and has like no generalization beyond that? That would be bad, right? So that's the question we want to ask about this thing. Like, are we inventing ideas that are super specific to the random k-SAT model? Okay. And this is some theme that I guess for the past few years I've been calling beyond average case analysis, which is kind of a wordplay on beyond worst case analysis. Where in some sense you can actually include a lot of things in this bucket. Like if you've seen smooth analysis of algorithms, that's an example of beyond average case analysis. If you've seen like robust statistics, that's also an example of beyond average case analysis. And today, this what I'm telling you about roughly fits in this area called semi-random models. And I won't tell you too much more about history, but that's also an area that investigates other problems like k-SAT in the same kind of setting. The idea is that you want to, on the one hand, escape NP hardness, so you want to do worst case. On the other hand, you also don't want to like find ideas that are super specific to a specific random model. So you want to do some kind of a hybrid in between, right? Like force yourself to somehow, not design something which is too quirky about a single random model. Okay, good. So the random model the model that we're going to look at for k-SAT is in some sense the most general model proposed in this context. It's called the smoothed CSP model. It was invented by Feige in 2007. Here is the model. It's very simple. You start from a worst case k-SAT formula. Okay. This is arbitrary, and then you do some perturbation to it. How do you perturb it? You go to every clause, okay? You don't change which variables appear in it. It's the same variables will remain. But each time you see a literal, you toss a coin with like some fixed constant bias, that's a 0.1, and if it lands on heads, you basically flip the literal. That's it. And you do it for independently for every literal in every clause. Make sense? That's the model. That's Feige's model. He's calling this literal perturbation smoothing. Okay, that's basically his idea. Now, if you think about it, because I'm smoothing every literal independently, it's not so surprising that, if I had some large constant times n clauses to begin with, the resulting formula should be highly unsatisfiable. So it is reasonable to ask the question we were interested in before. Like, if I give you a formula of this sort, can you basically refute it with high probability? Like, that most formulas in this model are going to be unsatisfiable. Can you actually find, short certificates of unsatisfiability efficiently? Make sense, the question? Good. So just to remind you, the clause structure, which variables appear in the clauses is completely fixed here. It's worst case. We have no control over it. The only randomness is, is in literals, and in some sense that arises only due to this perturbation. So there is, in principle, some information about the worst case literal pattern that you started with retained. Okay? Good. The model clear? Good. All right, so, I've got to show you another picture. I promise you this is the last picture. This picture is actually the best result we know in terms of algorithms for the model I showed you. And, if you think I just copied the picture from the previous one, it's true. I copied it because, it's the same picture. Okay, so the message is that actually you can find, so even though the algorithms that succeeded in those models and the analysis that succeeded doesn't work, the thresholds are exactly the same. Okay, so even though the model is more general, you can actually find algorithms that achieve the exact same results as random. So in other words, smooth model is no harder than random. Okay, that's basically the message. And so, yeah, that's the picture here. Just some history, doesn't matter too much. I showed you this work of Prasad and Satish Rao and Salil Shram. That was basically the trade-off for the yellow part of the curve for random case, and then Alan O'Donnell Whitmer was like the green part of the curve for the random case. When Feige invented his model, in some sense, the question he was worried about was that the ideas that people were able to use for random case did not quite extend. So he was inventing new combinatorial ideas, and so he was able to do something with it, but really not that much. But now, we basically get everything, okay? Okay, so just, this interlude about this second bullet point I showed you, like, this issue of Feige K-Mofek type certificates that exist below the spectral threshold. It turns out that actually we can now show that the same kind of certificates actually exist for just basically smooth formulas in general. So it wasn't, maybe one could have imagined that, it was a quirky aspect of the specific random k-SAT model, but it turns out it's not. It actually, the same phenomenon of existence of short certificates below the spectral threshold with the exact same delta case actually holds even for the smooth model. Okay? Yes?
So just to confirm, this time also that comment applies that while I have a short refutation which exists, finding it about time.
Yeah. Yes. Precisely. Good. Okay. So, I plan to tell you about this stuff a little bit more, but actually, I'm going to skip it because I'm going to tell you math instead of results. So I'll tell you a little bit about this and you can ask me offline about it, okay? So it turns out that, in some sense, maybe it's not so surprising that if I have to show something exists for like no matter what class patterns are in my formula, I have to prove a result which is like, in the realm of extremal combinatorics, right? It makes sense. In the random k-SAT formula, there was randomness. So you're trying to prove like something that arises by, chance, so to speak. But if you have to show that, some kind of a refutation exists in a formula, no matter what k tuples appear or whatever, you can see that it has to be some kind of an extremal question. It has to be like that, every dense enough hypergraph or every dense enough k-SAT formula has some structure. So it's an extremal combinatorial statement, and it turns out that there is indeed a precise extremal combinatorial statement that is at the heart of this result. It was conjectured by Feige. It goes by the name of hypergraph Moore bound because it is basically the trade-off between the length of the smallest cycle. It's a generalization of like the simple statement that gives you the perfect trade-off between length of the smallest cycle and the number of edges in the graph. If you ask like the same question for hypergraphs, that's basically the hypergraph Moore bound. And Feige conjectured it. It turns out that so basically with the same kind of techniques that we designed these algorithms with, we can actually also prove this extremal combinatorial result and therefore basically get this existence of polynomial size refutations. Okay, so I'm not going to tell you any of this. You can ask me later about it. Instead, I'm going to. So my plan is to actually tell you the spectral algorithm, or at least the idea of it. And remember, my underlying goal is to impress upon you that matrix Khintchine inequality is super cool. So cool that I taught an entire class about it. Okay, so that's my underlying goal here. So this diagram is to tell you like how the whole thing works because I'm going to focus on one single piece of it. Okay, so this is our goal. Okay, we wanted to invent algorithms that can refute smooth k-SAT formulas. Okay, now it turns out that there's a very standard reduction. I won't tell you. I guess maybe some part of it is non-standard, but it doesn't matter. There's a easy reduction to this separate problem called semi-random k-XOR. Let me explain what that is to you, and that's basically what we will focus on for the next 20 minutes. Okay, so k-XOR basically is a similar problem to k-SAT, but the constraints instead of being OR of literals is XOR of literals. That's it. Okay, that's the k-XOR problem. So it turns out that you can focus on k-XOR, and for whatever reasons, it turns which if you haven't seen them before, right now it wouldn't make sense, but you'll soon see like there is something interesting about them. They turn out to be the right predicate to focus on. If you focus on them, you get everything else kind of for free. Okay, so you focus instead of k-SAT, you focus on k-XOR. Yeah.
So like you assume SAT, for example, like This delta K that you had, can you prove that that's the
No.
vector?
Yeah, that's a great question. Yeah, we can go on for hours about this, but basically, like, there is a non-trivial relationship to n set about, with in some sense, you can think of this question that we saw as like an average case version of n set, non-deterministic set, which is like set on, I mean, I guess set is already ETH on steroids, so I don't know what to call n set. Some harder drugs. But it's like basically like, there is no short refutation. There is no sub-expert. There is no 2 to the Cn size refutation. 2 to the 1 minus delta n size refutation for, k-SAT formulas. So it's about like, size of refutation witnesses, and it's saying that, if I make k large enough, then it need to be essentially 2 to the n size.
So like the delta K you got in your result, you don't know that.
We don't know it. Yeah, it would be amazing if you could relate it to that. That would, then I would be, I mean, I don't believe in Seth either, but at least it shows something interesting is going on. Right now, it is simply a balancing point of 2 algorithms. So it's right now, I think the reasons are very dumb. Good. Okay. So like I was saying, we wanted to do smooth k-SAT. We focus on k-XOR. Semi-random just means that the literal patterns are just independent random. Okay. So semi-random k-XOR is a problem where which k-tuples appear is completely arbitrary, but after that, the literal patterns are completely random. You can think of them like, because it's an XOR, you can just think of it as a linear equation. Sum of k bits is like plus or minus 1. And then you can think of it as like the right-hand side, the plus minus 1s are like, or 0 1s are like completely independent random. Okay, that's semi-random k-XOR. Now, I in fact will just imagine that the instance we are given is a random k-XOR instance, and then just come back and tell you why we never use randomness. Okay, that's how I'll do it. This kind of a strategy will basically, eventually we'll realize that, we'll use like very specific aspect of random k-XOR formulas, which is this property of being well spread. Okay, I'll explain to you as we go along. And so, in some sense, you can think of it as like, this is the right pseudo-random condition, a simple pseudo-random condition, such that any formula that satisfies this property, you can more or less extend the right algorithm for random formulas to even these well-spread formulas. Okay. And then it turns out that, you can show that this is in some sense without the loss of generality by a decomposition theorem. Like basically, like, you can show that you can start from any k-XOR formula and like do some cleanup, reduce it to like some, a set of formulas such that each of them satisfies this additional pseudo-random condition. Okay. So you can think of it as like, every formula can be decomposed into pieces that are random like in the relevant way. And what that relevant way is, we'll see soon. Good. So, all right, so like rest of them, rest of them, I guess I'll explain to you later. I should say that, the spectral algorithms I'm going to talk about is based on a very important idea, which appeared in Piyush's title for my talk, did not appear in my title for my talk. I was debating this. I dropped the word Kikuchi from the title in order to dupe some people that they haven't seen this talk before. But anyway, like they are there here. The spectral methods that I'm going to use are based on certain matrices called Kikuchi matrices, and they were actually invented, for a problem called tensor PCA, which is a question in statistical inference by Alex Vine, Ahmad El Alawi, and Chris Moore. Okay, so we'll see how those matrices play a role. Okay, good. All right, so let's focus on the math. What we'll focus on is the case of 4 XOR. Okay. Why 4? Well, because 2 is easy. Okay, you might remember that anything to do with 2 happens to be easy, like matchings are easy, 2SAT is easy, blah blah blah. So 2 is easy. 3 is odd. Okay, and for whatever reason, odd numbers are hard here. So we chose like the smallest even number bigger than 2, which happens to be 4. That's the number theory aspect of this talk. So we'll do 4 XOR. And then I told you, like, I want to do semi-random, but I'll focus on random so that we have our intuition anchored throughout the talk. Okay, good. So now, let's focus on the right result. Remember, like, when do we expect a polynomial size polynomial time refutation? When it's like n to the k over 2. K is 4, so it's n square. Okay, so therefore, like, our goal now is, let's say I gave you something like n square random 4 XOR clauses. Okay, forget the epsilon squares. I'm pretty sure there is some log n that I'm missing, so I don't even think it's accurate. Our goal is to, like, find a refutation, find a proof, efficiently find a proof that convinces you that no more than half plus epsilon fraction of this constraint can be satisfied. Why half, by the way? Because a random assignment satisfies half the constraints in a k-XOR formula. Okay, so we are saying that no assignment does significantly better than random. It can only beat random by epsilon. Even for here. Even for k-XOR. In fact, you can say that this is what caused, well, yeah, same. There was a question I missed. Yes. Correct. Correct. Yes. Any other questions? Okay, great. All right. So let's focus on random 4XOR. By the way, the word tightly just refers to the fact that I want to get close to half. Okay, that's all I mean. It's tight because I'm getting close to what is clearly the threshold. Okay, good. So what do I want to do? So first of all, I want to think of assignments as plus minus 1 value instead of 0 1 value. The reason I do this is because even though 4XOR is a linear predicate over the the binary field, I want to do eventually my algorithms are like over real numbers. I'm going to do spectral computations or whatever. And then it turns out that this plus minus 1 representation is like somehow beneficial, like better. Okay. Good. So I'm going to think of plus minus 1 basis or plus minus 1 world of the assignments. And then if you try to write down what it means to satisfy a 4XOR constraint, in the plus minus 1 world, addition mod 2 simply becomes taking product. Okay? You can think about it, right? Like each time I multiply a new thing, like, if it's an opposite polarity, it flips, etc., etc. So it's not hard to see. So 4XOR constraints are simply monomial constraints. Okay? And now you can see why 4XOR is nice. Like you can think of any predicate as a polynomial, and 4XOR is the monomial. So if you wanted to do something about polynomials, it's not unnatural that you first figure out what happens for monomials and then hope that whatever you do for monomials extends. That's the logic. I'm not kidding you, that's more or less the logic. Okay, so 4XOR constraints look like monomial constraints. They're like product of some 4 bits out of my n variables is plus or minus 1. Okay, that's how it looks. Good. Okay, so an instance of this 4XOR formula is described by which 4 tuples appear. I'm going to call that a 4 uniform hypergraph H and a set of bits, 1 for every hyperedge B sub C. Okay, that's basically your data. When you're given a 4XOR formula, that's what you're given. Okay, again, feel free to stop me. Good. All right, so yeah, I mean, we are allowed to, but today you're not allowed to keep things simple. Okay, like, otherwise the thresholds get interesting and all. Yeah, so yeah, it makes sense to have less than equal to 4 and all, but let's say exactly 4 for now. Cool. Okay. One last bit of setup before we start discussing some ideas. I'm going to observe this trivial fact that I can write down a homogeneous quartic polynomial. Given a 4XOR formula, this polynomial computes the advantage over half of an assignment x. Okay, so look at what's happening here. I'm going over all possible 4 tuples in my hypergraph. For each 4 tuple, I compute the monomial corresponding to the 4XOR formula, and I multiply it by its right-hand side. Okay, and then I sum it up over the whole hypergraph. So what happens if you fix an assignment x, and if x satisfies the constraint, then the monomial will evaluate to b sub c. So b sub c gets squared. Square of a plus or minus 1 happens to be plus 1, another number theory fact. So you're basically collecting plus 1 for every constraint you satisfy, minus 1 for every constraint you dissatisfy. So you're basically getting like the advantage over half, right? Like, and then I'm normalizing so that the number is between 0 and 1. So if x satisfies the whole formula, you will get 1. If x dissatisfies all the constraints, you get minus 1. And if x does half, you get 0. Okay, good. All right. That was setup. So our goal now can be described as simply certifying or proving or finding a refutation witness for certifying that phi x is at most epsilon for every possible plus minus 1 vector x. Okay, good. All right. So here is an idea. It's a very cool idea. If you have seen this before, it sounds like whatever. It seems obvious, but it wasn't obvious at some point. And like Gert and Krivolovich are the people who invented this very cool idea that began like this whole field of spectral refutations. Their idea was like, I have a quartic polynomial. Okay, I want to upper bound it. Before Gert and Krivolovich, people were basically doing combinatorial tricks to analyze such things because they thought k-SAT and k-XOR are combinatorial objects. Okay. Gert and Krivolovich said that I'm going to think of phi x as a quadratic form of some matrix and use spectral upper bound from the matrix and hope that this will give me some new angle. So, here is their idea, in more detail. Here is their observation. Consider the following matrix, okay? It's indexed by pairs of individual variables on rows and columns. There are n choose 2 rows and n choose 2 columns. And then in the row ij and column kl, so ij kl entry, I write down b ij kl, the right-hand side of the equation with 4 tuple ij kl, if it exists. Otherwise, I write down 0, okay? If you now compute the quadratic form of A on the vector x circle 2, x circle 2 means the n choose 2 dimensional vector where the ijth entry is the product of xi and xj. So it's the degree 2 homogeneous quadratic monomials in x vector, okay? The claim I'm making is if I compute this quadratic form on A of this x circle 2 vector, then correctly scale it, I basically get phi x back. Okay? Yeah, x circle 2 is the n choose 2 dimensional vector, is indexed by all possible pairs of variables, ij, and in ijth entry, we simply write down xi times xj. So given a little n dimensional vector, I construct an n choose 2 dimensional vector as follows. Make sense? Good. So that's my phi x. Why is it true? It's very easy, okay? If you just like expand this quadratic form, okay, I'm gonna get ijth entry of this guy, klth entry of this guy, and aij kl. Okay, that's what I'm summing up. Only ijkls that have non-zero entries matter. So only ijkls that appear in my formula matter. And each ijkl, if I do the combinatorics right, appears 6 times because there are 4 choose 2 ways to split a 4 tuple, right? So that's like this 6. So I'm counting, for each ijkl, I basically get like 6 copies of it here, and then I just scale it back and normalize, so I get the same. Okay, you okay with this? Good. Okay. So that's Px, and their observation, Gert and Krivolovic's observation was that this is the quadratic form of a vector, and I can upper bound quadratic forms in terms of the spectral norm. Okay, so here is the upper bound. So I just say for any vector, there doesn't need to be an assignment vector. For any vector, I can upper bound this quadratic form by the L2 square norm of the vector I'm taking the quadratic form over times the spectral norm, or the largest singular value of the underlying matrix A. Okay, so that's what this upper bound is. Okay. But the great thing is x circle 2 is a plus minus 1 vector because x was a plus minus 1 vector. So the L2 square norm of x circle 2, no matter what x is exactly a fixed quantity, namely n choose 2. Okay, namely the dimension of the vector. So that's what I am ignoring constants here. Okay, so this is n choose 2 over 6m, which up to constant is n square over m times the spectral norm of A. Okay, you all good with this? Okay, very good. So I'm going to note it with an eye for the future as 1 over the average degree of this matrix A times the spectral norm of A. Let me explain what this is, okay? Think of A as a graph. It is a signed matrix, but think of wherever there are non-zero entries as edges of this graph. So there are n choose 2 vertices, and there is an edge between ij and kl if ij kl appear as a hyperedge, as a k-XOR clause, okay? Then, what is n square over m? Well, what is m over n square? Let's think about it. I had m clauses. There are n choose 2, vertices. So up to constants, each row on average has m over n square non-zero entries. I'm going to call that quantity d average, the number on average of non-zero entries in a row of A. And then I'm observing that all I have here is 1 in d average times the spectral norm of A. This is the normalization I believe would make things easier to follow. Okay, I'm doing this just so that you have some intuition anchored in. Okay, the way to think about it is d average, at least the largest degree, d max, is a trivial upper bound on the spectral norm of A. That's the reason I'm writing in terms of d average. Okay, because it's a fact. If you haven't seen this before, take it from me that the largest possible L1 norm of any row of a matrix is an upper bound on its singular value, largest singular value. So d max, because it's a plus minus 1 entry matrix, d max is always an upper bound on the spectral norm. And we have like this d average over here, so it's going to be like some combinatorial comparison eventually. Okay, good. But anyway, in order to get like an upper bound here, I have to compute or understand what this spectral norm of A will be, right? So in this case, notice that A is a matrix with essentially independent entries. Why do I say essentially? Where there are 6 copies of the same entry, there is clearly a dependence, right? Ignore that for a second. Each entry is independent because my XOR instance is random. The right hand sides are random and independent. So the entries of this matrix are independent. If you're worried about 6, just like keep one canonical entry for a IJKL. Drop all the other 5. Okay? It does not change anything because we already lost constants here. Okay? Good? Makes sense? Ramesh, it makes sense? Yeah. Okay. Had to call out someone. And okay, because it's a matrix with independent entries, we know everything about them. This is like a topic in classical random matrix theory. We understand, the spectrum of A to like gory details. We understand how the edges behave, etc., etc. So we can ask, random matrix theory people, what is the spectral norm of A? And they tell us an answer, very good answer. They say that, in this case, I'm going to just quote their result. It's very easy, by the way, but I'm not going to prove this to you. That the spectral norm of such an A is at most square root log n, the dimension of the matrix. Notice that it should be log n choose 2, but log n choose 2 and log n are basically the same up to constants. So that's what this is, okay? Times square root of d average. This is using the fact that it's a random graph. So even though there are some degrees which are too large, on average the degrees are small, and it turns out that d average up to a log n governs basically what the spectral norm is going to be, okay? So now, notice what's happening. I wanted to prove that phi x is at most epsilon, okay? So my goal is to prove that this expression is at most epsilon. The upper bound I have on the spectral norm of A is root of d average times root log n. So if I put it all here, I get root of d average times root log n divided by d average. So I have like root of log n divided by root of d average. So as long as d average is a large enough constant times log n, I can make it tinier than any epsilon. That's what basically this comment says. You're all good with this? Okay. So that's it. So, what does d average being bigger than log n mean? That m over n square has to be bigger than log n, so m has to be at least n square log n. Okay, so that's basically what this is. Okay, so I kind of lied in the beginning. I said n square over epsilon square. It's really n square log n over epsilon square. Good. This was all very easy. We're going to ramp it up a little bit, like, go level 0.5 instead of level 0 now. Let's say we want to do this yellow part of the curve. Let's say we want to, prove Prasad's result. Okay, so what we're going to do is like prove Prasad's result for 4 XOR today. Okay, we want to get like this n to the order L time algorithm that succeeds if m is n square over L. Okay. Say it again. I actually got an upper bound on the absolute value because I proved a spectral norm upper bound. It was already unsigned. Right, like, you see what I'm saying? Like the upper bound I wrote, when I took the upper bound, the spectral norm upper bound, there is already an absolute value. Yeah, good question. Good. So let's say we want to do this. Now we want to go below n square. You have less than n square clauses. I still want to refute. Okay, makes sense. So now, you can ask what to do. Okay. First, notice why the previous thing doesn't work. Can someone see why doesn't the previous thing work? Notice that d average is now less than 1. Okay. In order for the proof to work, this is the reason, by the way, I wrote it in this language so that the intuition becomes easy. Okay. In order to win, we have to make the spectral norm of A much less than d average. But if d average is less than 1, I claim that this is simply impossible. Why? Because there is at least one non-zero entry in the matrix. There is some row with at least one non-zero entry. You cannot make the spectral norm less than 1. So if d average is less than 1, you are basically done, right? Like the spectral norm and d average is no longer coupled. Okay. So anyway, like, once the density of the matrix becomes less than 1 entry per row, this thing clearly cannot work. Okay. So that's exactly what happens if you go below n square. The density of the matrix we just used goes below 1. So, that thing doesn't work. So what should we do? Well, we should have to invent like more complicated, more interesting matrices, which is exactly what Prasad and Slil and Satish Rao did. I'm going to call their matrix, I don't know if Prasad agrees with this, but I'm going to call their matrix symmetrized tensor power matrix without explaining what it is to you. You can ask me later what it is. Basically, like, they wrote a matrix whose quadratic form is phi x to the 2L, like, some power of phi of x instead of phi of x. Okay. Now, and then, in some sense, to me, it looks like a heroic analysis of this matrix because it is kind of complicated. I hope you not disagree, Prasad. Okay, it's kind of complicated, somewhat complicated for me. And the reason it's complicated is because it's like, it's a matrix with lots of correlation in its entries, right? Like, in some sense, it's a big matrix because it represents phi x to the 2L. And the same entries, somehow has correlation with many others. So it becomes a difficult combinatorial analysis, et cetera, et cetera. And so, they analyze, in some sense what the spectral norm of this matrix is, with some difficult methods. But here, because of like somewhat complicated nature of this matrix, they had to rely quite crucially on the randomness of the k tuples that appear in the k-XOR formula. Our goal is to go beyond it. Our goal is eventually to write down something that makes sense for like arbitrary hypergraphs H. So, this got us into trouble, okay? Or at least I couldn't see how to make this one work. So instead, I'm going to show you like a much simpler matrix that will at least allow us to recover this case of random like in 5 minutes, okay? Let's do that. What we will do is instead of writing phi x to the 2l as a quadratic form, we will still write phi x as a quadratic form, okay? Just as before. But this time I will write phi x as a quadratic form of a huge matrix, okay? Let's see what happens. So I'm going to write it as a quadratic form of n choose L by n choose L matrix, okay? My matrix is going to be the following. It's a very natural generalization of the previous idea if you think about it. Instead of thinking of a matrix which is indexed by pairs of variables, I'm going to think of a matrix which is indexed by L tuples of variables for a parameter L, okay? And L will grow beyond 2 now. It will be larger than 2. In fact, like L is going to be n to the epsilon, so it's going to be exponential size matrix eventually. That's fine, whatever, okay? Okay, so those are the rows and columns, and what are the entries? Well, S and T have a edge between them, or A of S comma T is non-zero if the symmetric difference of S and T happens to be a 4-tuple C. Okay, so in the matrix AC, imagine that it was a one-edge hypergraph, namely C. Then the matrix that is associated with it is the matrix where S and T are connected if and only if their symmetric difference happens to be this fixed 4-tuple C. Okay, just to like filibuster a little bit and let you give some time to digest this, notice that S and T are huge. They are L tuples. There could be like root n tuples for all I care. Their symmetric difference being 4 means that they have to basically intersect on L minus 2 elements. In the remaining 2 elements, they basically have to cobble together the 4-tuple that they are interested in. Okay, so in some sense, even though this is a huge matrix, the non-zero entries are kind of relatively rare, right? Because S and T have an edge only if like S and T basically, agree in all but 2 elements. Okay, makes sense? Okay, great. So that's my AC matrix. Okay, then I'm going to think of the matrix associated with phi as a signed combination of ACs. I'm going to write it as sum of B sub C times AC. Okay, where B sub C is the right-hand side of the equation where C was the 4-tuple. Yeah? Any questions? Good. All right. So just to note one simple property, notice that AC, in any row of AC, there can be only one non-zero entry. Because, if S has an edge corresponding to C, then S delta T has to be C, okay? But S delta T is just like addition mod 2. So S plus, in terms of the characteristic vectors, S plus T has to add to C. There can be only one, if at all, T that can make this possible, okay? So either there are no entries in a row or there is exactly one entry in a row. In other words, you can think of AC as a adjacency matrix of a matching, right? It's a matching as a graph, okay? And we can in fact calculate how many edges there are in it. Also simple combinatorics. How do we do that? Well, how do I decide? How do I choose? How do I know if S has an edge on it? How do I know if how many different pairs ST are there such that S and T are of size L and their symmetric difference is C? Well, the way I can do it is, first I decide the L minus 2 elements which are outside of this 4-tuple. That's really n minus 4 choose L minus 2. So sorry about that, but doesn't make a difference. And then, there are 4 choose 2 ways to split the 4-tuple and place one pair in S and the other pair in T. You agree with, up to this typo of n minus 4 here, you agree that this is the number. I'm going to call that number delta sub L. Okay, so we know the size of these matchings. Okay, good. Okay, so now, we can do the same trick that we were doing earlier. We can write phi x as a quadratic form. Phi x is, okay, look what I'm doing here now. I'm taking the quadratic form over A of the vector x circle L. X circle L is what you think it is, okay? It's the vector of L-wise monomials, L-wise homogeneous monomials in X, okay? And now, because each AC has delta L copies of C, I divide by delta L to keep one copy. And then I normalize by M just so that the number is between 0 and 1. So I have done exactly what you would expect, okay? Yes, Padmapriya. Sure, yeah. There is no idea. It's just like nomenclature. All I'm saying is that in this matrix AC, so it's a 0, 1 matrix, so you can think of it as an adjacency matrix of a graph. And then, for any row S, there is exactly one. If S has any non-zero entry, it can be exactly one non-zero entry, because it cannot be that there are two different T1 and T2 such that S plus C is T1 and S plus C is T2. That's not possible because of how addition works. That's it. Okay, so because every row has at most one non-zero entry, it's an adjacency matrix of a matching. It's a symmetric matrix, so it's a adjacency. Yeah, good. Okay, all right, perfect. So okay, good. So that's basic. So I explained to you why this is true, and then I use the same spectral upper bound. So I got this. Notice that the L2 square norm of X circle L is n choose L. So that's what this number is now. Okay, you're still with me? So remember what we did in the previous slide? We got to this point and we had n square over m, and then we interpreted it as 1 over d average. Let's do the same thing here. Okay. Let's compute the average degree of this matrix A. A is like the sum of ACs, the graph underlying, the support of the non-zero entries, okay? There are little m edges, little m, 4 tuples. Each 4 tuple contributes delta L edges to the graph. So in total, there are m times delta L edges. There are n choose L vertices. So the average degree of the graph is m times delta L divided by n choose L. Okay, so that's what this number is. And if you do the combinatorics, remember delta L has like a n choose L minus 2 term up to constant, that's what it is. And if you do the combinatorics, n choose L minus 2 over n choose L is L square over n square, okay, up to constant. So that's what this is. Any questions about this part? No? Great. All I'm going to observe, this computation we'll use later, but just notice this part, okay? You can see that this is the inverse of this expression, okay? So this is 1 over d average times the spectral norm of A, okay? The reason I'm saying it is because just like before, in order to prove that phi x is at most epsilon, I have to prove you that this expression is at most epsilon, which means that I have to somehow establish that the spectral norm of A is much less than d average, which is just like before. But this time, there are gory correlations in it. It's not a random matrix at all. Okay, each entry is an n choose L matrix. Each entry is copied n choose L minus 2 times. Okay, that's like some extreme amount of correlation if you think about it. And yet we are looking for a bound which would have been true if every one of its entries was independent. And it's going to be true. Okay? But of course, we can't hope to win with like classical random matrix theory. So this is the point where we introduce first tool. Okay? So we'll introduce like this, very beautiful, very important matrix concentration inequality, which will basically just seal the deal for us. Okay, so this inequality is called. Was that a question? No. Yeah. Yes, we're going to use that, of course. Yeah. So yes, it's very important. That's why it works, of course. Yes. Well, I just wanted to just clearing the naive intuition that you can get random matrix-like bounds even when there is great amount of dependence if there's structured dependence. Good. Yeah. So this is and this will make it possible. So this is the matrix Khintchine inequality. Sorry, what? No, okay. So let's compute it. Okay. So I'm saying each 4 tuple contributes delta L edges by definition. N minus 4. Yeah, but the 4 doesn't matter. N choose L minus 2 and n minus 4 choose L minus 2 are same up to constants. Actually, I think, yeah. It's n minus 4. So you think of compare n minus 4 to the L versus n to the L. N square. Yeah. Good. Yeah, no problems. Yeah. Please feel free to stop me. I will lose you at some point, but this is not the point. Okay, so yeah, so let's do the matrix Khintchine inequality. Okay, so here's the inequality. Actually, don't read this. Okay, let me remind you of the classical Khintchine inequality first, and then we'll go back and read it. Okay, so this classical inequality is trivial. It's so trivial that you don't usually call it the Khintchine inequality, and that's the reason. Khintchine inequality is like the pth moment version of this, technically speaking. But let's go with it. Okay, what's the inequality? It says let ai's be arbitrary real numbers. Okay. Then, if I choose random signs b1, b2 up to bm, take the sign combination of bi, ai. sum them up, okay? We want to understand how does the absolute value of this, random variable behave in expectation, okay? And this inequality says that it basically behaves, if you compute the expectation of like this absolute value, it looks like some AI squared to the 1/2, okay? Let me explain why this should have been obvious to you, okay? For a second, imagine that B are not plus minus 1, but Gaussians. Okay, this is a great trick, by the way. If you don't know this trick, you should do it all the time. Each time something seems difficult about signs, replace them by Gaussians. Usually it works out, and then you can go back to signs. So let's make the B bar a Gaussian. Okay, let's make it a standard Gaussian vector. Then if I look at GIAI, then it's like the inner product of a Gaussian vector with A. We know the distribution of such an object. It is a Gaussian. It's a scalar Gaussian. We know exactly its variance. It is the L2 square norm of the vector A. And so what this is simply the standard deviation of that Gaussian. Okay? If you remember, if I compute absolute expectation of absolute value of a Gaussian, it is square root 2 over pi times the standard deviation. That's what this squiggly thingy is hiding. Okay? So yeah, there is some constant in there. And then we are saying that, the signs don't change much, and you can prove it. Okay? So it's all very easy. Nothing is hard here. Okay, so you can think of like this theorem at the top as basically the matrix analog of it. Okay, and it's like a word-for-word generalization. Just replace small letters by capital letters. Make A1 capital A1, A2 capital A2, and so on. Okay, and now they are n by n matrices instead of 1 by 1 scalars. Take their sign combination. Instead of taking the absolute value, take the spectral norm and take the expected spectral norm of this object. That's what we are going to be concerned about. Let's syntactically write down what this right-hand side is. Okay, so I just squared the matrices because I squared the numbers. Then I added them because I added them. Now, addition of matrices unfortunately is not a number. So I have to produce a number. I take the spectral norm of it. Okay, and I made a mistake here. There should have been a 1/2. See, I copied wrong. But you can see, if you know the Khintchine inequality, you can guess the matrix version easily. So basically, it is what you would get by generalizing this, except for this square root log n term. Okay? Because the matrices are high dimensional, there is a dependence on the dimensionality of the matrix. But depending on how you think about it, it is surprisingly mild. It is only square root logarithmic in the size of the matrix. Okay? So that's what this inequality is. It says that up to square root log n, the matrices basically behave as scalars. Okay? They have their variance parameter, just like there is a standard deviation parameter in this scalar world, and that's what it is. Okay? Now, let me say, a couple more sentences about this Khintchine inequality in order to, help you maybe digest it a little bit more. So, you could ask, is this root log n necessary? Okay? And so it's an exercise you can think to the end of the talk, and at the end I'll answer it if you want me to tell you. Try to find an example which proves to you that this root log n is necessary. Okay? I claim it is necessary, that this inequality in principle cannot be improved. Okay? I claim that there are very easy examples of AIs where this root log n in fact is necessary. So you cannot hope to improve it. Okay? So, okay, that's great. But here is an important point. I just told you that this root log n seems surprisingly mild. Okay? Let me now contradict myself. This root log n is the source of all the problems. I mean, it's the source of some solutions, but all the remaining problems are caused by this root log n. Okay? So we'll come back and see how at the end of the talk, at the end of the second talk, you'll see why this root log n is like a major problem. And one way to get over several of the problems that I don't know how to solve is to understand when and how this root log n can be improved to something smaller. Okay? And I'll tell you a precise conjecture that would imply interesting results. Yes?
Probably just confused, but previously when you have this A matrix with this X tensor 2,
yes,
said something like A is like almost a random matrix.
The n square by n square matrix.
Yeah.
Yes.
Okay, this is something to. I mean, I guess my question is, for that matrix, you don't need to say.
Because if the entries are sufficiently, let's say if the entries are literally independent, then the classical Wigner matrix theory applies, and you can. There is no log n there, for example. Yes. Well, in the setting I am working in, there is log n there because I know what you're recalling. But notice that these are sparse matrices. So the number of non-zero entries in each row are fluctuating, and so the log n just arises because of that here. So in the setting I'm working in, the root log n is real, even in the n square case. but for like a silly reason, just because, it's the same reason that Prasad was worried about, some vertices of high degree. Yes.
I was refreshing my memory, like.
Sure.
So the following is a fact, but I don't know if it's relevant.
Okay.
If you have a matrix, if you have a graph on vertices that's irregular.
Yes.
And you take the adjacency matrix.
Yes.
And you put random signs.
Yeah. Then there is no root log.
there's no-
Yeah, that's the bilineal result. And all I'm saying is that the regularity is important there, right? Like I'm in the elder Shreni setting and not deregular setting. That's all. Yeah, very, very good question. Yeah. Yeah. Good. Any other questions about this part? Yeah, great question. So, it turns out, by the way, everything is in my course, but turns out, yeah, I got to advertise. Understanding expectations of the random variables and understanding their tail behavior are just two disjoint problems with like two different techniques, and arguably the second task is a much easier task. Okay, so you can prove sub-Gaussian tail bounds basically very easily. Let's like by some tensorization fact and things like that. Like there's a very easy proof of sub-Gaussian tail inequality in a very general situation. It's in my third lecture. So the tail bounds always hold. And so in some sense, once you estimate the expectation, you basically get the tail bounds for free. Okay. Now you could really ask like, what is the tail bound governed by? Like what is the scale parameter? And then of course it gets more interesting. But with the natural scale parameter to get like Chernoff like thing, it's very easy. Yeah. So they're all sub-Gaussian. So they're e to the minus t square kind of tails. Good. Any other questions so far? No. Okay, great. So let's continue and apply this inequality. Okay. Remember, we are trying to bound the spectral norm of A. And our target is to beat d average because our expression was 1 over d average times the spectral norm of A. Okay. So we apply the inequality. A was a sum of BC ACs, right? So signed sum. We know matrix Khintchine inequality says that, again, I'm missing a 1/2, sorry about that. Sum of C AC squared to the 1/2, right? That's the variance parameter. Then there's a dimensionality parameter. It is square root log of the dimension of the matrix n choose L. You already see why this is hurting us more than one might think. Our matrices are huge. Okay, it's not root log little n, it's root log n choose L, which, because L is going to be root n or whatever, this is not, ignorable parameter anymore. Okay, that's basically what's going on. Good. So root log n choose L is like about root of L log n because n choose L is like n to the L, let's say, right? And now, let's come back to this fact that we all discussed. AC was a matching. Okay, if AC is a matching, here's a simple fact. What's the square of a matching? What's the square of an adjacency matrix of a matching? It's a diagonal matrix of basically degrees. It's a diagonal matrix where you have 1 in every vertex that participated in an edge and 0 otherwise. Okay, that's all that is important. And you can square an adjacency matrix to see if you don't agree. Okay, you all good with this? Okay, so if I sum AC squared, I'm basically adding the degrees. Okay. So I'm going to get the whole sum is going to be a diagonal matrix, and on the diagonal are going to be written the degrees of vertices. Okay, what are my vertices? My vertices are elements of n choose L. So basically, this is a matrix of n choose L dimension. For every S, I just write down the degree. How many edges does it participate in? That's pretty much it. Okay, good. All right. So if I use a naive upper bound, again, I'm missing 1/2 everywhere. I'm really sorry about that. I made slides last night and I'm jet lagged. That's my excuse. So, okay, it should have been 1/2 here. And yeah, I guess I brought in the 1/2 here correctly, but did not write it here. So I have this diagonal matrix of degrees. The spectral norm of a diagonal matrix is the largest diagonal entry, which, we can call the max degree. So that's d max. And I just took like the square root of it. Okay, that's it. You all good with this? Okay, very good. So, it's d max, but it would have been great if all the degrees were equal. It would have been great like if the matrix was regular, because then d max is as small as it possibly can be. D max cannot be tinier than the average degree. The best it can be is the average degree. Let's hope for the best. Let's hope for the best and assume that there are no outlier degree vertices. Okay, so let's hope that it is d average A. And lo and behold, you are done if this is true. Why? Because we got exact same kind of expression that we got in the n square by n square matrix. There we had root log n times root d average. Here we have root L log n times root d average. Root L log n is just the root of the log of the dimension of the matrix. Okay? So when do we win? Well, we have this d average expression conveniently written down over here. Remember I told you that I'm going to use this ml square over n square formula. It's not equality, it's squiggly equality here. So I have ml square over n square. That's the d average. In order to, basically make 1 over d average times the spectral norm of A much tinier than epsilon, I need to make sure that this expression is much tinier than d average, which happens if d average is much bigger than, again, I have typos, I'm really sorry. D average has to be bigger than L log n, okay? So d average has to be bigger than L log n. D average is written over here. So ml square over n square has to be bigger than L log n, and you can resolve that very easily. I can give you 15 seconds to verify, but it turns out to be n square log n over L. So it's like extremely transparent, nothing really major happens, okay? So this basically gets you the 4 XOR result, okay? So we basically, okay, there is one cheating I did, I just claimed this to you, okay? For random hypergraphs, this is a fact. Okay? It should not be so surprising. It requires some thought to prove it, but Chernoff bounds suffice, okay? There is no high-tech machinery required here, okay? So I'm not like trying to give you a proof of this, because if you're clever and use Chernoff bounds, they suffice for proving this. That, there are actually, honestly, there are some vertices which are at too large a degree, but not by too much. Like you can prove that all the vertices have degree at most d average times log little n, okay, just by Chernoff bound. And then, with some extra log factor loss, you can just complete the proof here. You can be clever and not lose that log, but let's not worry about it. Okay, that's pretty much it. Okay. So I gave you essentially honest to goodness complete proof of the random 4 XOR refutation result here. Okay. Yeah. Well, we're going to come to that. Yes, but basically, right, like, the well spread out condition is a condition on the hypergraph, which implies approximate regularity of like the Kikuchi graph. Like, the degrees that matter are the degrees in this Kikuchi thingy, like this n choose L dimension thingy. The well spreadness is a condition on the hypergraph. And it's not immediate, but it is true. So we can prove it that if the hypergraph is well spread, then, the degrees actually do concentrate. Okay, so and well spreadness just, for the sake of completeness, well spreadness just means that, if I look at any variable, it should occur in roughly the same number of 4 tuples. If I look at any pair, it should occur in roughly the same number of 4 tuples. And because like I'm less than n square, really like, the average frequency of a pair should have been less than 1. So, all it means is that no pair should occur in more than, let's say, log n 4 tuples. That's pretty much it. That's what well spreadness means. The point is that it's a very weak control on the hypergraph. It's not like some, global control. It's a very local control. It's like some analog of regularity of a graph, except that I have a hypergraph now. And that is sufficient to imply regularity of this Kikuchi extension. And so this proof just works. Good. Any other questions here? Good. Okay, great. So we've done this. I don't know what this arrow was pointing towards. Sorry about that. Yeah, I guess it doesn't even appear. So I clearly messed up there. Okay, so the message of this part of the talk is that matrix Khintchine allowed us to easily prove that the spectral norm of A is as small as it would have been if all of its entries were independent. Okay, so if you haven't seen this before, then this should be like a non-trivial, powerful takeaway. Okay, good. So, let's discuss, the semi-random aspect before we go further. Where did the randomness of the hypergraph appear? Let's go back and ask, where did we use it? We used it, but where did we use it? Well, there's only one spot where the hypergraph mattered, which is in estimating how the degrees of this, this Kikuchi graph are distributed. That's all the usage of the hypergraph was. And, like we were discussing, basically, like, we just need this Dmax is about D average condition, which I'm going to call approximate regularity, which I hopefully, makes sense. And if not, it's not so hard to see that the spectral norm of A would blow up. So, that's a problem. But it turns out that even if your hypergraph does not satisfy this, you can do some tricks to basically not worry too much about it. So in this case, in fact, you can show that even if like there are some vertices of too high a degree, just by like some Markov-like thing, there cannot be too many of them. And then you can show that, therefore, even though the spectral norm is large because of those rows, the spectral norm is large. The quadratic forms that are really large are sparse vectors. And why are we not concerned about sparse vectors? Because the vectors x circle L are completely spread out. No coordinate is larger than any other. While the quadratic forms that are blowing up are the ones that we don't care about. So if there was a way to really care about flat vectors where all the coordinates contribute the same mass, then it would have been okay. And it turns out that there is a way to actually efficiently bound flat quadratic forms using semi-definite programming or whatever. doesn't matter, we can do it. Like there are multiple ways to do it now without losing log factors. So if this last 20 seconds did not make sense, don't worry about it, but just take my word for it that we used the randomness of the hypergraph to do something very weak and something that we can account for by other methods even if it does not hold. Okay, any rough questions about this part? Good. Okay, so let's discuss a little bit, like 15 seconds, about the odd arity instances. We did 4, but what about 3? Okay. So, there is a problem at the outset because the matrix we define does not make any sense. Okay, like, if you have, it's a fact of how addition mod 2 works that, if I add 2 sets of same size, their symmetric difference is always even. Okay, again, a number theory fact for us. So, we can't create like, odd arity matrices this way. We do something. So what do? There are many ways to do it, but basically like, all of those ways involve converting a 3 XOR formula to a 4 XOR formula. How do you do it? Well, you basically take 3 clauses that intersect in a variable and, basically derive a new clause by cancelling the one that they intersect on. Okay, you're observing that if x1 plus x2 plus x3 is something and x3 plus x4 plus x5 is something, then you can add the equation and addition of x3 plus x3 is 0. So you get a 4 clause. Okay. We'll see this, well, I guess we won't get to it, but this is very simple idea. It's called like XOR resolution or whatever. And this creates an evenality thing. So you can take the Kikuchi matrix or whatever for this derived instance. Of course, you complicate your life a little bit now because independence is lost, right? Every new constraint corresponds to 2 old constraints, so the right-hand sides are now correlated. So to work a little bit harder, in fact, like you to design some new machinery. Most of the parts in that big diagram I showed you were to handle odd. That's just how life is. But it, works out, okay? In fact, like it turns out that even for the random case, the approximate regularity doesn't hold, which was so easy, but because of the dependence created by these derivations, the approximate regularity is simply false. But it turns out that, it's still almost true. Like, there are some rows which are large, but they are very small fraction, and you can like somehow throw them away once and for all, and then show that the rest of them are regular, at least for random 3 XOR formulas, etc., etc. Okay. And again, like, you can show, and this is again a little bit more complicated because, we are working with like these derived constraints, but it is still true that if you start with a 3 uniform hypergraph with small spread, then the lift of it to 4 uniform hypergraph, by taking pairs of constraints, and then taking the appropriate Kikuchi matrix gives you a regular matrix or approximately regular matrix after throwing away some outlier rows. I won't tell you how to do this, but there is some combinatorics involved in proving such results. Good. All right. So now I still have. Yeah. Okay. Good. Okay. The larger of the 2 applies. Okay. Yeah. So yeah. Okay. So I want to like set up what I want to tell you in the next part. Okay. Is the pace okay? Okay. Good. I want to like set up what I want to do in the next part, which is to show you how this method that somehow seemed kind of specialized to KSAT and k-XOR like problems actually has applications to problems that don't seem like algorithmic questions at all. Okay, this is what I want to explain to you next. So that's what like this method of spectral refutations in combinatorics is. This is what I also call the Kikuchi matrix method, but I have grown out of that words now. I don't know, I bored myself by calling it that, so I'm calling it something else now. So anyway, like the idea is to solve some problems in extremal combinatorics by proving, unsatisfiability of XOR formulas once we've gotten very good at, right? Like in the past hour or so. So good. All right, let's do it. So let me first give you a high-level spiel for why this should make any kind of sense. Then I'll give you some example applications. Then I'll set up like the application. We'll come back and do the math, in the next hour. Okay, good. So here is the very high-level spiel. There are many questions in coding theory, in combinatorics, etc., etc. Actually, there is a very recent and nice application to date, such a lower bounds to the same idea, and I'll also tell you about it. They all basically involve showing that a certain kind of combinatorial object does not exist. Okay, a code of some property doesn't exist, or a hypergraph with a short cycle doesn't exist, or whatever. Like you're interested in proving that something is absent. What you do is you construct a family of XOR formulas, family of k-XOR formulas, such that each of these formulas is satisfiable. In this family, every formula is satisfiable if and only if the combinatorial object satisfies the property you're looking at. So you somehow encode this fact of satisfying a property as a family of XOR SAT formulas being satisfiable. Okay. So if you want to prove, if you successfully do this encoding, then in order to prove that there is no such object, all you have to do is like one member of this family is unsatisfiable. Right? If the first line is correct, then the second line is just a trivial corollary. Okay? Which member should we show unsatisfiable? Well, let's try a random member. Why not? If we have a family of formulas, we to show one is unsatisfiable. Let's pick a random member and try to show it's unsatisfiable. Now, this suddenly makes the problem more, probabilistic. We can try to like do union bound, Chernoff bound, whatnot. There is a snag. Okay, it would have been very easy, except for the fact that union bound and Chernoff bounds, etc., will not work. Why not? Typically in these encodings, and this is the hard part, the number of random bits that are required to sample a formula from this family, or you can think of the size of the family equivalently speaking, is much tinier than the number of variables on which the formula is. So for example, imagine that I have a n variable formula. Okay? In this world, the number of random bits required to sample it would be much, much tinier than n. In fact, in some applications, as small as logarithmic in n. Okay? So it's like you have very few random bits. You want to still somehow, union bound over 2 to the n assignments. That's impossible. Like if you wanted to run a union bound argument, you are in trouble because there are 2 to the n assignments to union bound over. In order to win, you will need a tail bound of 2 to the minus n, but you can't have a 2 to the minus n tail bound, at least naively, if you only have r random bits. The best tail bound you can expect, any event that happens has to happen with like 2 to the minus a number of random bits probability. That's just how probability works, right? So you can't hope to argue that this random member is unsatisfiable by naive probabilistic analysis. Okay. The punchline is that even though these non-constructive Chernoff bounds, etc., don't work, what you can do is analyze the algorithms that we develop for refutation. You say, I don't know if this formula is unsatisfiable, but I can analyze my algorithm and try to see if it will succeed in refuting. If my algorithm succeeded in refuting, well, the formula must be unsatisfiable. So it's like, I established the unsatisfiability of my formula by running an algorithm and making sure that it outputs unsatisfiable. Okay? And the intuition is that, Chernoff and union bound methods are like, in some sense, they are kind of making complicated reasoning. Like, on the one hand, they are very simple, but they are very general. So they are like, they can deal with unsatisfiability of all sorts of kinds. But algorithms are simple. If they work because there is some simple structure in your input. You're saying that, simple structures can possibly be fooled by a small amount of randomness. You can't expect this to be true in general, but algorithms, if they're simple enough, can possibly be fooled by a small amount of randomness. That's like the high level intuition. And so, that's basically like, why you can expect this whole method to actually help you. Okay, good. So, yeah, I think this is from a time I gave a talk at a proof complexity conference, which this isn't. I should have written algorithms. I forgot to make appropriate changes. Good. Okay. All right. So yeah. So this is this is maybe some things I'll tell you before finishing. So let me tell you like some applications. So I told you about this hypergraph mode bound, or I guess I hinted at it, but I never described to you. And then these two applications I actually plan to cover, but given the pace, I'll actually just tell you about two. Unfortunate part is that if I don't tell you three, I don't get to tell you about the second tool, which is super important and super cool. So please ask me offline. But there are more applications. There are applications to like strong forms of similarities theorem. If you know, similarity has this like many of you might have heard of similarities regularity lemma. That lemma is called a lemma because in the paper that he proved it, there is a theorem, of course, right? And the theorem is that if I take a dense subset of integers, meaning like a subset of integers that has a constant density inside the first n natural numbers, then such a dense subset must contain an arbitrarily large arithmetic progression. Okay, so in some sense, the cool part or the reusable part of this whole machinery was the regularity lemma, but this was the theorem he was after. It's a very deep, very important theorem. I think at least 3 Fields medals have gone to different proofs of this result. Okay, so it's a very important result, and there are several well-studied variants of this similarities theorem, which also turn out to be super important. This strong form is about restricted APs, which is like, I don't want dense subsets to contain an arbitrary AP. I want them to contain an AP where the difference set, the common difference, is from a small restricted subset. And then the question is, how small can you make this subset? Okay, these are called restricted versions of similarities theorem. I still have 3 minutes, 4 minutes, 5 minutes. Okay, good. Yeah. So these are called restricted versions of similarities theorem. And like, the key question here is like, what is the smallest size of the common difference set that will still keep similarities theorem true? And so, there is a conjecture of Bourgain, I guess, from the 80s that some, polylog n suffices. We are very, very far from proving polylog n, and the best bounds we know are polynomial, but we can improve the polynomial with, the same kind of machinery. Okay, so good. And, this very recent, very nice paper of Oliver Curtin, Russell Impagliazzo, and Tony Pitassi, they actually show how to actually get state-of-the-art data structure lower bounds by Kikuchi and all the matrix concentration stuff. It's kind of amazing. It turns out that the object they required was exactly semi-random CSP refutation, and so yeah, the whole thing just like fit right in. Cool. Okay, so I'm only going to tell you about well, I guess I probably only tell you about the second application here. But you can of course ask me offline about any of the others appearing on this list. Good. Cool. Okay. So now I have 3 minutes. I can stop and like, bank my 3 minutes for the next. Is that okay? Okay. All right. Okay.
Do you have any questions? Okay, so we'll break for coffee and then resume at 4:12 p.m.
Yeah, sure, yeah. So here is what similarities theorem says, right? Like it says that, let's say, similarities theorem is for arbitrary k, but let's just think of 3 terms. It's called Roth's theorem, and it's like a precursor. So it says that, there is a large enough, there is some fixed but large enough n0, such that if I take any integer bigger than n0, okay, and then look at the set of numbers from 1 through n, integers from 1 through n, take any subset of these integers which has a constant density. Okay, so it has a constant fraction of elements, then such a set must contain at least one 3-term arithmetic progression. Okay, that's what the similarities theorem, actually Roth's theorem says. And similarity basically says that the same thing is true for arbitrary k. Okay, just like the threshold n0 changes, but like everything else is the same. So now actually, there is a density version of this theorem which says that not only is there one 3-term AP, but in fact, the correct fraction of 3-term APs is present. Like if the density of my set is delta, then you expect delta squared fraction of all 3-term APs to be in there. Okay, if I estimated it correctly. And what this density version of similarity says that in fact like delta squared fraction are present. So here's the question now. This delta squared fraction in principle can use whatever common differences there be. Okay, so in principle it can be that for some dense set they use some set of common differences, for some other dense set they use a different set of common differences, and so it is possible that if I restrict the common difference to a small set, then there is some dense set that does not contain any 3AP with those prescribed set of common differences. Okay, so this theorem says that such a thing does not happen. It says that suppose I pick a random set of size little m for a parameter m. Okay, and then I want to prove that with high probability over the choice of this random set, for every dense set, there should be a 3-term AP with a common difference from this random set. And I ask, what is the threshold m for which this is a monotone property, so it has a threshold, whatever. There is always a phase transition here. You can ask, what is the smallest m for which this result holds? And so the conjecture is that m is polylog of n. In fact, it's like exactly log to the k minus 2 of n if you're looking at k-term APs. And so the state of the art, which is due to this Kikuchi business, is for 3-term APs, n to the 1/3 suffices. So previously it was n to the 1/2, and now it is n to the 1/3. Yeah. In fact, like the problem I'm going to tell you about in the next part is actually strictly harder than this. Yeah, so we'll solve a problem that implies this result. Good.